Good morning. This week's lab is looking at static equilibrium. We have been looking at static equilibrium in class, and we're going to be looking at a couple of measurements here. A couple of measurements that seem a little funny, possibly. The first measurements we want to do are using what we call a force table. So we'll get a better view of this when we go and set this up and take a look at the measurements being made. But it's just a platform, and then on the platform there are different angles at which you can place strings, and then the strings are exerting some kind of attention. Now, one thing I got to be careful with here, you got to make sure that these mounts along the edge are secure, that they're flush against the edge and they're secure. And then, you got these pulleys with very low friction, and I've got a hanger sitting here. I have a second mount I'm going to use here. And then I have another hanger. I'm going to put a string here. And then what I want to do is I want to measure the mass of this object. Now I know what you're thinking. You're thinking, well, go set it on a scale. But that would be too easy, right? We could use static equilibrium. What I could do is I could take this object, place it along one of these strings. I hope. Maybe not. There it is. So I've got one object. I want to find out what the mass of this object is equal to. So I'm going to try doing that by adjusting the tensions on these two sides. So when we're in static equilibrium, what I'll be able to see is that all of the strings, there are three strings here going on, all of the three strings are going to pass right through the center point. Now right now that's not happening. There is actually this post in the middle that helps hold things in place while we're doing the measurements, and I've got that in place right now. Let me see if I can find some weights that we could bring up here and try using. So I found some. I found a couple of 100-gram weights. So I'm going to put a couple of 100 grams on here. Now there's already 50. The hangers themselves are 50 grams. And then I'll put a couple of 100 here. Oh, when I do that, look, now it's pulling too much. So what I could do is I could adjust the angles. So that's the way the force table works. What we can do is we can put 3 or 4 strings up here. Right now we're only working with 3. And the idea is this. With the force equilibrium table, we adjust the tensions. I'm going to call this one T. I'm going to say that is my sample. So I'm going to take this sample and place that along one of the strings. Now the tension that we set up with that is going to be given by mg. And then what we'll do is we'll pull these other two strings at angles with different masses. Now, remember that not only can we adjust M1 and M2, but adjusting theta 1 and theta 2 is going to make a difference also, a big difference. And in fact, sometimes it's easier to do the adjustments in terms of angles. This is actually looking pretty good. In terms of angles. So I'm going to move this angle a little bit to here. I'm not changing the masses right now. I already put a couple of masses on there. I have like 250 grams here, 250 grams here. I could go in and measure those, and it's not quite at equilibrium. Oh no, it is. It's actually very close. Okay, so I can read off these angles now. So now there's a 360 angular scale set up on here, and it's kind of hard to see in the lighting here. But I placed the sample right at 0. And then I'm placing the opposite direction is right at 180. So the angles I want to measure are here and here. So this angle looks like 61 point something degrees. And this angle, right now at least, it looks like 57.5. So, and we're not quite at equilibrium. We could still fine tune this a bit. So once we get close to equilibrium, I can take the post out and just kind of push things around. If we're truly at equilibrium, then the strings will bring there's a ring here. It'll bring the ring back towards the center, and it will bring it back in a way where, again, all three strings, if I look along the three strings, they all pass right through the center. Okay, and the post makes that easy to see. So a top view, so here's a top view of what's going on. Here is my top view, and what it looks like I can do mathematically is say that mg is going to be equal to the x components of t1 and t2. So that would be m1g cosine theta 1, m2g cosine theta 2. Now these two sideways components, they also have to match, right? So that's another condition that has to be met, but we can actually measure the mass of the sample by saying that mg, the tension in this direction, equals the cosine theta components of the other two tensions. And we can drop the gravitational field stuff here, so that factors out. And again, that means that this would work on Mars, or Venus, or Mercury, or the Moon, right? We could go to any planet and set up our force table and measure masses this way. Can you say the same thing about the scales that we have? Good question. So these force tables are gonna work in any gravitational field. Now I factored out the g's because we don't need those, and it says that I can calculate the mass of these samples if I know m1, m2, cosine theta 1, and theta 2. So here's my data table. So for each one of the samples, I'm going to get a data table, and the data tables are going to have these different masses, and then they're going to have angles that I've carefully measured, and we'll take all the measurements in equilibrium. When we do that, what should happen is that when we read the masses that we've calculated here, those should all be pretty similar. What we would like to do is get at least 3 different sets of measurements for these masses. Now, right now, I've got the masses m1 and m2 that match. If m1 and m2 are the same, then that would say that theta 1 and theta 2 are the same. And that might be fun to try out for one of the measurements. But also what I want to try is I want to try some outside the box, stuff. Maybe I'll try something where one of the masses is quite a bit larger than the other mass, but we can compensate with that through adjusting the angles. So it's kind of fun to play around with the force tables and see how you can adjust the angles, and then the masses will change accordingly. So the results table is going to look like this. We've got our same samples that we've worked with before. We did densities on these the first week of the course. They came back. We did more measurements, right? It seems like we've used these a few times. So we've got the brass cube, and we've got the aluminum cylinder. Measure the mass of that. And we can measure, you could go back to lab number 1 and see what you measured for masses on there. But usually when we do this lab, the rules are no getting out any scales until we have all the measurements done. And then at the end of the lab, we get the scales out and see how we did. So you never know, this might catch on. Scales may go out of fashion. People may carry force tables around and go, oh, let me see, show me that object. I've got a force table right here. I think I could do some mass measurements using my force table. Okay, so the data tables look like this. The results table are going to look like this. The measured values are the ones that we're getting off the force table. And the accepted values will be the ones we get when we finally take these out and set them on the scales and see what the scales read. Sure, we're going to give the benefit of the doubt to the scales, I guess, is how this is going to work. And then we'll do percent differences on those. So that's the plan with each of these 3 objects. Now there's a second part of the lab, and that is once we get these 3 objects measured, what we want to do is we want to come back and measure the mass of what I'm calling a weighted stick. Now this is what it looks like up close. So it's like a meter stick that's been cut off. Now you would think that the center of mass of this would be in the middle, but somebody filled it in with some metal stuff right here. And what that's done is it's shifted the center of mass. Now, I was playing around with this trying to find the center of mass, so I don't want to take this off. But we do want to get the mass of the stick without this in place. So the mass that we're going to be measuring is, I'm going to go ahead and take this off, I guess. So I'm going to go ahead and take this off just to emphasize the point. And that is, we're trying to find the mass of this. Okay? And the way we're going to do that is we have a fulcrum. You know, everybody's got a fulcrum, everybody's got a force table, I guess. And what we do with this is we can take this support piece, set it on the fulcrum, and see how it bounces back and forth. So what we can do to start with is identify where the center of mass is going to be for this. So I'm going to go back to where I was, which I can't find now. Where did it go? It's around here somewhere. Okay, so let me see if I've got it. Almost. That looks pretty good, actually. So we could adjust it, fine-tune it just a little bit. Okay. But the idea here is this. What we want to do is we want to take this stick now that we've identified the center of mass. There it is. What we want to do is now loosen the lock on that, slide it over. So here's where the center of mass is located. I've got to write that down because I'm going to need that number. And then what I'm going to do is I'm going to move the stick over a ways. You know, I don't know, a few centimeters. And of course it doesn't balance anymore because there's a gravitational force on this side. I can treat the gravitational force as if it's all coming right from the center of mass location. And the center of mass location now is not over the fulcrum, but it's over here. And so I've got a normal force pushing up and I've got a gravitational force here. Now what I can do, and they're not lined up with each other, but what I can do is I can take one of these objects. Let's say that I take the aluminum, so I'm going to take the brass cube. So I'm going to take the brass cube off of this. And it's got its own little support, of string support right here. What I'm going to do is take the brass cube now. Wow, that's really pretty heavy. So I'm going to try and balance this in kind of an extreme fashion. Let's see if this works. Wow. Okay, I wasn't expecting it to be this. I guess I could have done it the other way, huh? Maybe I should have put the weighted part of the stick the other direction. All right, there we go. So there's one example of setting this up. I'm going to try it the other way. But what I've done is I've moved the stick so that the center of mass is now located over on one side of the stick by some distance. That distance is going to become a lever distance. And so I can now compare torques. I've got a torque coming from the brass cube. That's creating a torque. And that torque will be mg times r. Whereas the center of mass over here on the other side is creating a torque. Now, that's kind of interesting that the center of mass is keeping track of the entire stick. Even though part of the stick is over on this side and part of the stick's over here, I can still treat the gravitational force as if it's all coming from the center of mass. And so I've got opposing gravitational forces that are creating opposing gravitational torques. Now the support piece is staying in the middle. It's not moving. And that's why when we get the measurement here, it's only a measurement of the stick's mass. It's not a measurement of the metal piece. The metal piece hasn't moved in this. Okay, so the stick has been moved over. I've got to now go in, measure these two distances, which I got to be careful. I got to get a good ruler out and measure that right down. Probably estimate tenths of a millimeter, maybe, which is going to be hard to do. And then I'll try a couple different arrangements of this. But the idea then is to say that when the torques are balancing, then big M times big R, the cube times its lever distance, is equal to the stick times its lever distance, and then we can solve for the mass of the stick. Now, the idea that we want to follow up with here then is, let's do this once with the brass sample, the aluminum, and the lead. Now, what should we use for the mass of the brass, the aluminum, and the lead? And I'm thinking we use the measurements that we got from the force table, right? We're just imagining scales have never been invented. Instead, we've been using force tables to come up with masses of objects. So we know the masses of these because we did a set of measurements on the force table. And we're going to take the numbers we got from that and then apply them over to the weighted stick. Whoa, it doesn't balance. What happened? Wasn't it balancing better? I turned around and it was not balanced anymore. There it goes, looks better. Okay, so measure these three objects first, and then we'll switch over to this, and then we'll get the weighted stick, and we'll see how we do for the day. So again, this is static equilibrium, stuff we've been looking at in chapter 12, as far as balancing forces, and then balancing torques. So if there's any questions, let me know. I think we're ready to move on and take a look at the setup on one of the lab tables. Here are what the force tables look like when we're doing the measurements. So what I've done is I've taken one of the samples. You can see that there's the brass cube is right here. And that's being supported from one of the strings. And then I have two other hangers that I have placed. And I've put some weights on those. It looks like there's a couple hundred, maybe 250 on each one. The hangers themselves are 50 grams. And then it looks like the weights that I've placed there are each 100. And then what you can do is you can fiddle around with the angles, right? And so I did. I adjusted the angles. Now what I'm looking for is right up here, I'm looking for all three strings to pass right through the center. Looks like the alignment's almost there, maybe not quite. Maybe I need to fine-tune this a bit. But, and then if I do want to adjust the angles, I can reach out. I can loosen one of these supports, and I can slide this to the side. It was better alignment before, for sure. So maybe I want to move it back. And then as I move it back, I can pay attention at the center and see what's happening in terms of those strings. And again, once all of the strings line up and cross right, they all point right at the center of that post, then we are at equilibrium. Now moving on from this, once we've got measurements of all three samples, we've got the brass and the lead and the aluminum masses figured out, then what we can do is we can move over to the torque bar, and that's what I've done here, or what I'm taking a picture of right here. So what we have here is I have adjusted, the center of mass is over at the 67.2 centimeter mark. There's actually a pencil line there now. I guess I need to go back and erase that. But that's where the center of mass is located. Right there. And what I've done is I've used a counterweight. So I moved the support over about 15 centimeters. So I think for the aluminum I use 15, for the lead and the brass I use 20. And then I found a point where it balances. And this is pretty sensitive, so I can go in now, and if I move this just 0.5 millimeter or so, so again, let me just move this a touch, and it no longer has the torques that are matching up. So the torques no longer balance. I don't know that I'm going to be able to find that point again. But that's the idea, is going back and just kind of fine-tuning this. So we'll see. You know, I've got a set of measurements. We'll run those in the data, and we'll see how we did using the balance beam and the force table to measure masses of some of our metal samples and for the weighted stick. All right, if you guys have any questions, let me know. Take a look at the data sheets, see what you come up with.